So in this video, I just wanted to finish up on the factors affecting the reactions in electrolytic cells. The last thing I wanted to talk about is the nature of the electrode. All right, so again, the electrode is the piece of material that is stuck down into the electrolytic cell, and it can behave a little differently depending on the situation. All right, so I wanted to point out the difference between what's considered an inert electrode versus a non-inert electrode. All right, so in an inert electrode, essentially the key is that the material itself here does not partake in the chemical reaction that drives the cell, all right, or that is being performed by the cell. You can think of an inert electrode as just a highway for electrons. All right, on one side, its job would be simply to supply electrons to the solution or the molten salt. And on the other side, its purpose would be to accept the electrons. All right, and we'll talk about the opposite of this in just a second. But in order for it to be an inert electron, it's generally going to be some inert material. And so two common materials for inert electrodes would be platinum, and you probably know about platinum because it's a metal that a lot of jewelry is made of. And that kind of makes sense, because when you're making jewelry, do you want a metal that will react with the humidity or the oxygen in the air, or do you want a metal that's going to ignore that? All right. Well, if you want it to stay shiny, you want it to basically not react with the materials in the environment. So that same property is what makes platinum a good electrode for an inert electrode. All right. All it does is allow electrons to flow through it. All right, and those electrons would be able to be supplied or accepted depending on the side, but it's not going to react with the materials that are in the cell. All right, another common material would be graphite. And graphite is the same material that you have in pencil leads. All right, so the thing about graphite, it's pure carbon, but carbon has a couple of different forms that it can take, and the nature of the bonding of the carbon atoms in graphite is pretty special, in that it allows an electric current to flow through it. All right. Take note that there are some types of carbon, like a diamond, that are not conductive and would not have the same purpose or have the same properties, but graphite would allow that. All right. So one thing to note about inert electrodes is that from the time you start using them till the time you end, they're going to remain physically unchanged. All right. And to show an example of what I mean by that, I'm going to switch to the other type, which is a non-inert electrode. And I have to make some changes to the drawing. I drew this as an electrolytic cell, but I want to go back and draw this as a voltaic cell. All right, so to do that, first of all, we have to make this into two separate cells instead of one cell. So we can put a little barrier here. We can put a salt bridge in. That's what this thing is right here. And with the voltaic cell, remember the purpose is to create electricity, so we don't need a battery. All right, so you can take the battery out of the system. So we're going to have copper solution over here. This is going to be a copper anode. This is going to be a zinc solution over here. This is going to be a zinc anode. And what I wanted to draw your attention to is what happens at the zinc anode. All right, so remember that this is at the anode, and that's where the oxidation is occurring. And so what's happening in the oxidation? Well, in the oxidation, remember the reaction is that zinc it is losing 2 electrons, and it's becoming zinc 2+. All right, so the zinc 2+ floats out into the solution. The electrons that were there in the neutral atom flow through the wire. All right, so the key thing is that the atoms in the electrode itself are taking part in the reaction. So this is the half reaction of the oxidation. Where are these zinc atoms located? They're located in the electrode. All right. So the one thing about this is that as this reaction occurs, you're actually going to get a smaller and smaller electrode, because these atoms are going to go from their neutral form and then start floating out into the solution when they're in their ionic form. All right. So it's going to get smaller and smaller, and that can be contrasted against an inert electrode, where you would never have a change in the electrode because it doesn't take part. All right. The electrons that end up going through the cell are supplied by something in the cell. All right. Whereas the electrons that are supplied in this voltaic cell are actually supplied by an atom that's part of the electrode. All right. So these would not be considered inert electrodes. All right. So those were some factors that affected the types of reactions that you would see in electrolytic and voltaic cells. So what I want to focus on here are some factors that would affect the amount of products that you make. Not just what you make, but how much you make. All right. And the first is going to be the number of electrons flowing through the cell. All right. So if I just show the half reaction of this would be a reduction of sodium. All right. Notice that this requires an electron. All right. So hopefully this is not too far of a stretch. The more electrons that you have flowing into the cell, the more that this reaction can occur. All right. So that's because an electron is essentially a reactant in this reaction. All right. So a higher current would mean more supply of electrons. All right. And therefore you're going to make more products. All right. So in the same cell that you would be reducing sodium ions to make sodium, at the other side you might have some, let's say this is melted sodium chloride. You have an oxidation going on, and that involves electrons being pulled by the battery. So the same thing that supplies electron to the cathode is going to be the same force that pulls it away from the anode. So that would increase the rate on the anode side of the reaction as well. Okay. And the second thing is going to be the charge of the ions in the cell. So what I wanted to do here is just draw your attention to, or ask you to think about, what happens if we're doing an electrolytic cell to electrolyze sodium chloride. This is exactly what we did a couple videos back, where we had the melted sodium chloride, versus if we were doing the same type thing with magnesium chloride. All right. So what I want to do is draw the half reactions that you would be doing here. So if we were electrolyzing sodium chloride, the oxidation would be happening to the chloride ions. All right, so an electron is taken away from both of these guys, generating the chlorine molecule, and here are the two electrons that got taken away. All right, and in the reduction side, we've got two sodium atoms reacting with two electrons to make two neutral sodium atoms. All right, so one thing I just wanted to point out, you might be looking at this right here and saying, well, isn't that the same as 1 to 1 to 1? And the reason I did that is because I'm comparing it to the oxidation half reaction, and so I'm just trying to make it so that the number of electrons stays the same. All right. So the thing about this is when this is happening, a total of 2 electron transfer. All right. And what I mean by that is, well, at the same time we have 2 electrons taken away at the anode, we're going to have 2 electrons supplied at the cathode. Whenever we get that 2 electron transfer, notice it's going to create 1 mole of, or 1 molecule, I should say 1 molecule of Cl2, but it's going to create 2 molecules or 2 atoms of sodium. All right. So one way to make this true is if you said 2 moles of electrons would create 1 mole of Cl2 and 2 moles of sodium. All right. But by contrast, notice here that everything about these two things is the same except for this reduction reaction. All right. Here, what was needed to react with the 2 electrons was 2 sodium ions. All right, but since magnesium, melted magnesium chloride, the magnesium ion is going to have a +2 charge. All right, so 2 electrons are going to react with only one of these things to generate a neutral magnesium. All right, so therefore the difference is that whereas over here 2 moles of the electrons created 2 moles of the sodium, here 2 moles of the electron are going to create only 1 mole of the magnesium. All right, so and again, that all just has to do with the fact that for an individual sodium atom, it only needs 1 electron to get reduced to its neutral metal form. But if you're a magnesium ion, you need 2 electrons to become your neutral metal form, and that affects that means it's it's going to need more electrons than an individual sodium atom. All right, so So that does it for factors affecting electrolysis. We're next going to move on to a topic called electroplating, and I have kind of I don't have guided notes per se. I do have a section where I want you to answer some videos according to a Tyler DeWitt video that's posted on this, and it's actually a pretty good video, and it's linked on my Canvas site. So enjoy.